Okay, so in the previous video we learnt how to multiply matrices together and also talked about the conditions under which we can multiply matrices. So remember, the dimensions are really important. And today what we want to have a look at, or in this video we want to look at the applications or some applications of matrix multiplication. And this is where it's really important that you have a by hand understanding of how multiplication happens, so that you have a clear picture of what's actually happening with the numbers in that process, so that you can answer these kind of application questions. Okay, so let's have a look at a couple of examples through this video. So the first one, we have in a recent AFL game, the Bulldogs scored 10 goals and 6 behinds, and Carlton scored 7 goals and 7 behinds. This information is represented in the score matrix S. Okay, so obviously we've got the Bulldogs in the top row and Carlton in the bottom row, and we've got goals and behinds in the two columns. In the game of AFL, each goal is worth 6 points and each behind is worth 1 point. This information is represented in the points matrix shown opposite. So this is the number of points for a goal and this is the number of points for a behind. Okay, so we want to evaluate the matrix product SP. So remember, product is another word for multiplication. Okay, the product of two things is when we have multiplied those two things together. Okay, so if we're calculating SP, it is literally S times P, and we know from our process of matrix multiplication that we do row times column. Let's also think a little bit about dimensions. So this is a 2 by 2 matrix and this is a 2 by 1 matrix, so we know that our answer is also going to be a 2 by 1 matrix. Okay. Now, top row times the only column goes in the top row of the only column of the answer. And remember, when we're multiplying matrices, we're sort of imagining flipping this row around so that it's vertical next to the column and then multiplying those pairs of numbers together. So we're going to do 10 times 6 plus 6 times 1. Okay. And then when we do bottom row times only column, it'll be 7 times 6 plus 7 times 1. Alright, then we can work that out. So that's 60 plus 6, so 66. And 6 7s 42. Struggling this morning. Plus 7, so essentially it's 7 7s, so 49. Okay, so describe what is being calculated by evaluating SP. So if we think about what's happening here, where in each multiplication, so the purple multiplication, for example, we did 10, which was the number of goals, times 6, which was the number of points for a goal. So that's calculating the total number of points from a goal, from their goals. Plus, then we did 6, which was the number of behinds, times 1, which is the number of points they get for a behind. So what we're actually calculating here is the total number of points earned by each team. Okay. So the top row, the same in the S matrix, the top row was the Bulldogs' score. The top row here is the Bulldogs' total points. The bottom row was Carlton's score. The bottom row here is Carlton's total points. Okay, let's think about example 2. 2 triathletes complete some training over the weekend. Triathlete A swims at an average speed of 4 kilometers per hour, rides at an average speed of 35 kilometers per hour, and runs at an average speed of 13 kilometers per hour. Triathlete B swims at an average speed of 4.5 kilometers per hour, rides at an average speed of 32 kilometers per hour, and runs at an average speed of 15 kilometers per hour. This information is represented in the speed matrix opposite, which is called S. And so we have triathlete A and triathlete B represented in the rows of the speed matrix, and we've got the speeds for the swimming, the riding, and the running in the 3 columns. Each triathlete spent 30 minutes swimming, 2 hours riding, and 1 hour running. This information is represented in the time matrix shown below. Okay, so this is the swimming time in hours, the riding time in hours, and the running time in hours. Now it says use your CAS to evaluate the matrix product ST. We might use our CAS to get the answer, but I'm still going to write it out so again we can see what numbers are being multiplied together, and hence what is actually happening and what we're actually calculating in that process. 3215, so that's S, and we're multiplying that by T, which is 0.5, 2 and 1. Okay, so thinking about dimensions, this is 2 by 3, this is 3 by 1, so we're going to be able to do the multiplication, and the answer we get will be 2 by 1. Okay, I'll just leave room to write. Okay, so let's think about what the calculations will actually be. So the answer, if we multiply the top row by the only column, that's going to go into the top row of our answer matrix when we do top row by only column, and when we do bottom row by only column, that's going to go in the bottom row of our answer matrix over here. Okay. So in terms of the calculations that are happening, I'm going to write them out. We're doing 4 times 0.5 plus 35 times 2 plus 13 times 1 on the top, and in the bottom row we're doing 4.5 times 0.5 plus 32 times 2 plus 15 times 1. So if we think about what's actually happening there, we're taking the, so for triathlete A, we're taking, so that's the purple calculation, we're taking their swimming speed and multiplying it by the time they spent swimming. So that's giving, speed times time gives distance. So that's giving, saying we're swimming at 4 kilometres per hour for half an hour, and so therefore that's going to be 2, and that means we swam for 2 kilometres. And then we're going to add that together with the riding speed times the riding time, which gives the riding distance, and then we're going to add that together with the running speed times the running time, which gives the running distance. So what we're actually going to be calculating in the final matrix is the total distance that each athlete exercised for, that each athlete travelled over the course of the triathlon. Okay, so we can get our CAS. Now, obviously, if you're instructed to use your CAS, there's no one can know what it is you actually type into your CAS. So personally, having thought through those multiplications in order to enable me to understand what's happening, I probably would just type in at this point those two calculations: 4 times 0.5 plus 35 times 2 plus 13 times 1. That's 85, and 4.5 times 0.5 plus 32 times 2 plus 15 times 1, 81.25. Okay, so this is triathlete A and this is triathlete B. But of course you can actually put in the matrices, but again, quite often it's honestly more efficient to think through what's happening a bit yourself and then just do the number calculations rather than actually entering in the matrices. So we've got 2 rows and 3 columns, 4 by 35 by 13 by 4.5. Sorry, it's not by. We're not multiplying. Okay, and then your second matrix would be a 3 by 1, and it is 0.5 tab 2 tab 1, and indeed we get the answer that we got by just doing the 2 separate lines of arithmetic. So describe the meaning of the elements of the product matrix ST. So ST is our final answer over here, and the meaning of those elements, it's the total distance travelled by each athlete during the triathlon, during their triathlon training. Okay, so whilst they were training, athlete A did a total distance which incorporates swimming, running and riding of 85 kilometres and 81.25 kilometres for athlete B. Okay, next thing we want to talk about is summing matrices. So row or column matrices in which all the elements are 1 are called summing matrices, and that's because they can be used to calculate the sum of the elements in the rows or columns of another matrix. So for example, if we think about the 3 by 2 matrix pictured here, 6, 8, 7, 2, 5, 3, let's evaluate this matrix product. So that matrix multiplied by a column matrix of just ones. Okay. Now, in order for this multiplication to exist, this is a 3 by 2 matrix. If we want to multiply by a column by a column matrix, it's going to have to be a 2 by 1. We want one column. That's what makes it a column matrix. It'll have to have 2 rows in order for the multiplication to happen. Okay. All right. So when we do that, again, we're going to do row. So we're going to get a 3 by 1 matrix. We're going to do row times column. So it'll be 6 times 1 plus 8 times 1, which is essentially just 6 plus 8. Okay. The second row is going to be 7 times 1 plus 2 times 1. Again, that's just 7 plus 2. So we're adding up the row. And the bottom row is going to be 5 times 1 plus 3 times 1. So essentially, what we're actually calculating here is 6 plus 8, 7 plus 2, and 5 plus 3. So we are summing this matrix. Calculating this matrix product is actually summing the rows of the original matrix. Now obviously we're dealing in very small matrices by hand. What we need to be thinking about in the back of our mind is these are techniques and understandings that we're learning that would be applied in a much larger situation, a huge database of information, and there's a need to total up a row or total up a column, and ways that we can do that, or we can have a computer do that by sort of programming this matrix multiplication. So, you know, yes, okay, if we just want to add up those rows, we could do that much more quickly just by adding up the rows, but we're talking about techniques that are actually going to be able to be applied to much larger data sets, much larger matrices containing vast amounts of data. Okay, let's have a look at part B. This time we want to evaluate the matrix product where we're using a summing matrix beforehand. This time it's a row matrix only of ones, and then our same 3 by 2 matrix we had in the previous example. Okay. So this time, again, if we want to multiply by a row matrix when we have a 3 by 2, we can't actually put the row matrix afterwards. Okay. We couldn't have 1 by something after here. The multiplication wouldn't be possible. So we have to multiply, we have to have the row matrix before, okay, in order to make the multiplication work. And then the only way that we'll actually be able to make it work is if it has 3 columns, so that it will multiply by this 3 by 2 matrix. Okay, so if it's going to be a row matrix, it has to go before the matrix we want to calculate the product with, and if it's a column matrix like it was in part A, it would have to go after. Okay, if we had a column matrix, it'd be something times 1, and so therefore you can't multiply that by a 3 by 2 matrix. Okay, so it has to go, the column has to go after the matrix, the row has to go before the matrix. Okay, so let's do this multiplication. So we're going to have, we've got a 3 by 1 times a 3 by 2, so we're going to get a 1 by 2 matrix in our answer. And we're going to do our 1 row times our left column is going to go on the left, and then our 1 row times the right column is going to go on the right. Okay. Alright, so we're going to have 1 times 6 plus 1 times 7 plus 1 times 5 will be the purple multiplication, and then the green one is going to be 1 times 8 plus 1 times 2 plus 1 times 3. Okay, so what we actually have here is 6 plus 7 plus 5, the sum of the column, the first column, and 8 plus 2 plus 3, which is the sum of the second column. So 18 and 13. So the sum of the first column is 18 and the sum of the second column is 13. Again, thinking about this as a technique to apply to a much larger data set, a much larger matrices. So generally speaking, to sum the rows of an m by n matrix, so we just summed the rows of a 3 by 2 matrix by multiplying by a 2 by 1 matrix. Okay, so we used a column matrix 2 by 1, multiplied that by the 3 by 2 to sum the rows of the matrix, and we post multiply. The summing matrix goes after, okay, post rather than pre. Okay, so the summing matrix goes after the matrix that we want to actually sum the rows in, and it's going to be a column matrix. And obviously the number of columns in the first matrix, so the n has to be the same as the number of rows in your summing matrix. Okay, so to sum the rows of an m by n matrix, we post multiply by an n by 1 matrix filled with ones. To sum the columns of an m by n matrix, so we just had a 3 by 2 matrix, and to sum the columns, we had a row matrix before that. Okay, so it has the same number of columns as this one has rows. Okay, so therefore, if this was an m by n matrix, this would need to be 1 by m. So we pre-multiply. The summing matrix goes before the matrix that we're trying to actually calculate the sums of, by a 1 by m matrix. And again, that's a 1 by m matrix that is filled with ones, if what we want to do is sum. Okay, so let's have a look at an example with that. Again, we're picturing much larger data sets, but we'll use a simple example. The number of desktop and notebook computers sold by 4 stores is given in the table. Use a summing matrix to calculate the total computer sales per store. Okay, so if we want the total computer sales per store, yes, the total computer sales per store. So we want to know what is the total sales in store A. Doesn't matter whether they're desktops or notebooks. What kind of just the total computer sales. Total sales in store B. So we want to sum. We want to sum the rows. And yes, we can do that by hand very quickly. But the point is, we want to be able to what matrix calculation would be needed to do that. Okay. So when we want to sum the rows, let's go back up to here. We need to use a n by 1 matrix, so we need to use a column matrix, okay, and we're going to post multiply by that column matrix. So our original matrix of the store data is 10, 4, 4, 5, 5, 10, and 3, 2. Okay, this is store A, B, C, and D, and this is desktops and notebooks. So we're going to need a column matrix, and the column matrix, if we think about how big it needs to be, this is a 4 by 2 matrix. We're going to need this to be a 2 by 1 matrix. Okay, so column matrix with 2 rows and 1 column, so that the multiplication will work. Okay. Alright, so then we can do that. It's going to be 10 times 1 plus 4 times 1, so it's just going to be 10 plus 4. 4 times 1 plus 5 times 1, so 4 plus 5. 5 times 1 plus 10 plus 1, so 5 plus 10. And 3 times 1 plus 2 times 1, so 3 plus 2. And we are therefore going to get 14, 9, 15, and 5. And so what we have is 14 computers were sold at store A, 9 at store B, 15 at store C, and 5 at store C. Use the summing matrix to calculate the total number of desktop sales and the total notebook sales. So this time we want to add the columns. So this time we're going to need a row matrix beforehand. Okay. So remembering that we've got our sales matrix 10, 4, 4, 5, 5, 10, and 3, 2. So this is a 4 by 2 matrix. This has to be a 1 by something matrix. It's going to have to be 1 by 4 so that that multiplication works. Okay. And so when we do that, we're going to get a 1 by 2 matrix. And the first number will come from doing the only row times the left column. Be 1 times 10 plus 1 times 4 plus 1 times 5 plus 1 times 3. And then only row times the right column will be 1 times 4 plus 1 times 5 plus 1 times 10 plus 1 times 2. And so we are adding the columns, 14, 19, so it's 22, and 9, 19, 21. So remember they were desktops and notebooks, so 22 desktops were sold across the 4 stores and 21 notebooks were sold. Okay, desktop computers were priced at $1,500 each, $1,500 each, and notebook computers at $2,300 each. Use matrix multiplication to find the revenue from the sales in each store. Which store has the highest revenue? Okay, so again, let's get our sales matrix. 10, 4, 4, 5, 5, 10, 3, and 2. Okay. So what we want to do is calculate the the dollar value that we sell in each store. So store A, store B, store C, and store D. Desktops and notebooks. So we need to think about how we're going to multiply. We want to multiply all the desktop values by 1,500 and all the notebook values by 2,300. And again, this is important that you understand how matrix multiplication works. So what we want to do here is we're going to post multiply by the prices, 1,500 and 2,300, because what this will do is when a row multiplies the column, we're going to do 10 desktops times $1,500, which is the desktop price, plus 4 notebooks times $2,300, which is the notebook price, and then that's going to be giving us the total sales value of the sales from store A, which is what we want. Okay. Alright, so let's do that. So I might get my CAS to do the multiplication for me here. But we could do them all individually, but we're going to have sort of quite a lot of numbers and the numbers are getting kind of big. So perhaps we'll do it this way. But it's important though that you understand how those numbers are being combined together. So we've got 4 rows and 2 columns. 10, 4, 4, 5, 5, 10, 3, and 2. And then we are multiplying that by, and we've got a particular template for the 2 by 1, 1,500 and 2,300. Okay, and we get 24,200, 17,500, 30,500, and 9,100. Okay, so you can absolutely do that by hand. This number would have come from doing that purple row times the purple column I've got circled, so that would have been 10 times 1,500 plus 4 times 2,300 to get that number there. Okay, this number here, row times only column, would be 4 times 1,500, so that's the total desktop price, total desktop revenue, and then 5 times 2,300, so that's the total notebook net revenue, etc. Okay. Which store has the highest revenue? So we can now see from our matrix which gives the total revenue that store C has the highest, okay, which is that one there. Can't spell today. Store C has the highest revenue, which is $30,500. Okay, and the last thing we want to have a look at in this section is displaying simultaneous linear equations using matrices. So we'll talk further down the track about how we use the matrices to solve simultaneous linear equations, but for now we just want to look at how they can be represented using a matrix. So matrix arithmetic offers an alternative way of solving the equations. As I said, we'll look at how we actually do that down the track. And again, 2 equations with 2 unknowns, there are much simpler methods to use for solving those rather than matrix methods, but we're envisaging systems of equations where we've got many more than 2 variables and many more than 2 equations, and thinking about processes by which they can be solved. So if we think about this matrix equation here, alright, if we expand out the left hand side, so rows times columns gives us 2x plus 1y, row times column gives us 5x plus 3y. We haven't changed anything on the right hand side, okay, we're just expanding out the left. So we get, 5x plus 3y and 2x plus y equals 4, 8. And then if those two matrices are equal, if you've got, AB equals CD, the only way that that's true is if A equals C and B equals D. Okay, so the same logic applies here. If these two matrices are equal, that thing has to be equal to that thing, and that thing has to be equal to that thing. And so we get 2 equations, 2x plus y is equal to 4, and 5x plus 3y is equal to 8. So when we come to solving simultaneous equations using matrices later on, we're going to need to be able to reverse this process. How do we turn the simultaneous equations into the matrix equations? So here, for example, we've got another set of simultaneous equations. 4x minus 2y equals 3, negative x plus 6y equals 5. And they can be represented as a matrix equation in this way. Okay, so essentially the square matrix of numbers, we call that the coefficient matrix. That's the coefficient of x and y. So 4 times x is the 4 there. Negative 2 times y is the negative 2 there. Negative 1 times x is the negative 1 there. And positive 6 times y is the 6 there. It's really important before you turn the matrix equation into, the simultaneous equations into a matrix equation, that you've written them in the same form. So in both matrix equations we've got the x terms first, then the y terms, then the equals, then the numbers, okay? And that's how we're going to construct the matrix. So the 4x4 matrix then just comes from the coefficients, and then we're multiplying by x and y, okay? Now, if you rearranged your matrix equations at the beginning, your simultaneous equations at the beginning, and you put the y terms first and then the x terms, then your 2x1 matrix there would be yx. But I would say conventionally always arrange them in alphabetical order, x terms, then y terms, then whatever, and then your column matrix here should also be in alphabetical order. And then simply 3, 5 becomes a column matrix 3, 5. Okay, well, as I said, we'll talk more about this simultaneous equations process down the track. We just really want to be able to recognise that we're getting the same thing here. So example 4 is show that by multiplying out the matrices in this matrix equation, we can generate the simultaneous equations shown there. Okay, so let's multiply out the left-hand side here. So we're going to have, and because we need to show that, we're going to need to actually do it by hand to show what's happening. It's not enough just to type it into your calculator and say, oh yes, look, the answer matches your answer. Okay, so we're going to have 1 times x plus 2 times y plus 3 times z in the top row. Middle row times only column gives us the middle row here. So that's negative 1 times x plus 0 times y plus 2 times z. And then the bottom row times only column, 3 times x minus 2 times y, or plus negative 2 times y, and plus 0 times z. Okay, and that's still equal to 147. We haven't changed the right hand side, we've just multiplied out the left. Tidy up the left hand side is x plus 2y plus 3z. So I'm just going to make that a bit bigger. Negative x plus 0y, so there's no 0 there, plus 2z, sorry, no y there. And then 3x minus 2y, and then 0z, obviously there's no z. And so that is equal to 147. And therefore then that must equal that, that must equal that, and that must equal that. So there's our 3 equations. X plus 2y plus 3z equals 1. Negative x plus 2z equals 4. And 3x minus 2y equals 7, which is exactly what we were trying to show up here. Okay, so as I said, we'll revisit simultaneous equations further, a little bit further down the track. So the work today is the remainder of exercise 11D, questions 4 to 11.